thins. Metallicity gradients flatten as if a spoon stirred the disk, the warm halo collapses, the circumgalactic pantry is gone, and inside-out quenching follows. The stripped creature looks like a jellyfish only for a while. In reality it is a city losing its aqueducts. Without the inflow that once fed molecular clouds, the star-forming engine sputters. Radiation from newborn clusters and the X-ray bath of the cluster itself harden the spectrum that bathes every system within. The milieu is not merely photogenic, it is erosive. Planetary systems orbiting their host stars ride through this gale with stellar gravity as their seatbelt, but their climate control is rewired by the environment. Protoplanetary material around young stars is truncated, older systems lose shielding as the interstellar neighborhood thins and becomes hotter, making cosmic rays and hard UV more penetrating. Bow shocks form ahead of stellar winds, magnetospheres are compressed, sputtering and charge exchange chip at the top of atmospheres. Where high-energy photons flood upper layers, hydrodynamic blow-off can take hold, energy-limited escape carries light gases away, dragging heavier species when heating is intense enough. Hydrogen leaks first, oceans become a source for the sky as sunlight splits water and the lighter partner drifts into space. Oxygen and oxidized minerals remain, a deceptive residue that can mimic a biosignature while signaling only that hydrogen was lost faster than chemistry could bury the surplus. With each pericenter passage through the cluster's dense core, the flux spikes, the loss ticks upward, and the clock on habitability advances. As the host's gas disk is shaved down and then stripped outright, replenishment pathways for volatiles close. Cometary traffic from the outskirts dwindles because the outer reservoirs were the first to be torn away. Clouds that would have seeded rains and moderated climates never form. Planets that might have balanced on the line between blue and brown pivot toward aridity. Seawater concentrated into brines leaves salt flats where tides once ran, evaporite stack like geologic ledgers of a vanishing hydrosphere. Iron-rich dust, scoured from desiccating soils and rusted by the leftover oxygen, turns the air into a red veil that can lift for weeks, then fall in ochre drifts. Mountain snowlines retreat and disappear as greenhouse cycling first intensifies and then stalls when the working fluids are gone. On tidally locked worlds around small stars, nightside CO2 frost caps grow and shrink with seasons that are now driven more by dust opacity than by water. On faster rotators, global storms resemble a Mars scaled up, deep convective chimneys at the equator, planetary-wide dust lanes, lightning that crackles through powder-dry skies where rain no longer closes the loop. The same tails that glowed with newborn clusters become laboratories of erosion. Massive stars in the wakes pour out Lyman continuum photons and winds that act like sandblasters on exposed atmospheres in their light cones. Cosmic rays from supernovae within the tentacles lace through planetary magnetospheres, generating auroral ovals that are beautiful and expensive in terms of chemistry. Nitrates accumulate, ozone layers are punched and repaired and punched again. Over millions of years, what began as ecological stress hardens into a new geologic era. Rivers carve no new deltas, only dust streaks. Basins that once held seas become bas-reliefs of polygonal mud cracks and shorelines etched into stone. Silicate weathering, the thermostat of temperate worlds, slows to a crawl because there is neither fresh rock exposed by rainfall nor enough liquid to carry ions to the basins. Tectonics, if present, keeps moving continents, but in vain. The water cycle that made mountains green is now a memory lodged in fluid inclusions and in the isotopes of the last stubborn hydrates. Outside and quenching of the host and inside-out desiccation of its worlds rhyme with the same cause. When supply chains of cold gas are severed, stars stop forming and seas stop cycling. The galactic metropolis that flashed its jellyfish filaments across the cluster sky leaves behind a quieter, redder disk, a population of aging suns, and an archipelago of deserts revolving in orderly silence. Telescopes would read this history as a pattern: truncated gas disks, suppressed star formation rates, hard radiation fields, and exoplanet atmospheres trending thin, oxidized, and mineral-tinted. The image is not dystopian, it is instructive. Clusters are weather systems, and weather writes landscapes across every scale. In the same way that a single sand grain remembers the wind that moved it, a dune remembers a season, and a desert remembers a climate, a dead sea on a distant world remembers the day its galaxy grew tentacles and the sky began to bleed. Cluster weather is patchy rather than constant, so the scouring comes in pulses. As the host sweeps through cold fronts and merger-driven shocks, ram pressure spikes and ebbs, tails kink, then re-straighten, eddies in the wake alternately compress and erode clumps. Thermal conduction tries to evaporate the stripped clouds while radiative cooling fights back. Viscosity and magnetic draping suppress some instabilities and amplify others. In a single orbit, hundreds of millions of years, the galaxy can pass from a bright, knot-studded comet to a barer, redder disk with only a faint afterimage of its former supply lines. In the nucleus, asymmetric torques and pressure gradients funnel what little gas remains inward, igniting accretion onto the central black hole. Jets and ionization cones carve through the already thinned medium and add a hard, time-variable glow to the radiation budget seen by every solar system downrange. The same flow that tore away the pantry also switched on a lighthouse that bakes the shoreline. Around individual stars, astrospheres shrink because external pressure rises. Where the stellar wind once inflated a roomy bubble, the intracluster gas presses closer, termination shocks move inward, neutral atoms of the surrounding medium leak into the heliosphere and seed pickup ions that change the chemistry of the wind itself. Magnetospheres of planets are squeezed and more tightly coupled to the upstream flow, current systems strengthen, auroral ovals widen. Charged particles find shorter, more direct paths to the upper atmosphere. Every magnetotail becomes a windsock that snaps under gusts from cluster weather rather than only from its parent star's moods. On worlds with thin shields, non-thermal escape joins thermal escape, sputtering, ion pickup, and polar outflows nibble at the top of the air even when sunlight is low. On hot dayside hemispheres of close-in planets, helium triplet absorption at 1083 nanometers would deepen as blown-off gas forms a cometary shroud, sodium lines weaken because alkalis ionize. Transit spectra would show a dryness that is hard to mistake, muted water bands at 1.4 micrometers and 6 micrometers, strong CO2 at 4.3 micrometers, excess O2 collision features and ozone that together signal oxygen without oceans to balance it. CO alongside O2 would be the telltale of photochemistry unconstrained by a hydrological cycle, a mirror of oxidation, not metabolism. Volatile logistics fail from the outside first. Kuiper belt analogs and wide Oort-like clouds are the earliest casualties. Their weakly bound comets are stripped into the intracluster light or ground down into diffuse dust, so late deliveries of water to the inner system all but cease. The reservoirs that once rained small corrections onto climate become a diaspora of grains reddening the cluster core. Inner asteroids survive but run dry, impacts deliver heat, not hydration. With every million years, the carbonates and hydrates that locked away earlier atmospheres record declining exchange with the sky. Volcanoes continue to write in basalt and sulfur where interior heat allows, but the handwriting becomes spidery as volatile fluxes drop. Some planets drift into a CO2-dominated greenhouse that ends not in steam but in stagnation. Others overshoot into high-albedo dust eras where reflected light cools the surface until the dust lifts again, a chaotic dance whose period is set by storm physics rather than by oceans. Milankovitch-like cycles persist, but their expression is filtered through dust opacity and thin air thermodynamics. The last rains are local, convective, and bitter. They etch tree-ring patterns in evaporite terraces and then stop. Not every world succumbs equally. Massive super-Earths with deep gravity wells clutch their air and become pressure-cooked deserts with tropospheres thick enough to move heat but starved of water to move life. Subneptunes shed their hydrogen skins and step down the mass radius diagram toward rocky cores, their transition accelerated by the added EUV and by the shrunken astrosphere that no longer buffers particles. Tidally locked planets around cool dwarfs keep permafrost on the night side long after the day side has gone copper and ochre. Katabatic winds spill glacial air into basins, carving dunes that march under a thin sun. Icy moons fare better underground than on the surface, sputtering scours their exteriors, but pressure and radionuclides can sustain brine oceans behind kilometers of ice, a last refuge where chemistry remembers how to be busy. These enclaves are durable but isolated, like aquifers beneath a continent that has forgotten rivers. From afar, a quenched disk with tentacular scars would broadcast its planetary census statistically. Thermal phase curves of hot, thin-aired worlds show brutal day-night contrasts. Light curves of temperate planets acquire storm season flicker as dust lifts and settles. Polarimetric slopes steepen because fine particulates dominate scattering. In transmission, water bands fade across many targets in the same neighborhood, while oxygen dimers and sulfur aerosols rise, an ecological signature written at the scale of an environment, not a species. Direct imaging with future coronagraphs will find continents that are too bright and too steady, the glint of seas absent even when geometry is favorable. Spectral maps of intracluster filaments will correlate hardened radiation fields with the driest planets, drawing a weather chart whose isobars span hundreds of kiloparsecs. The physics is sober, but the narrative is not defeat. Clusters are apprenticeships in scarcity. Civilizations, if they arise before the last rain's end, would learn to husband volatiles, to roof entire valleys against dust, to quarry ice from shadowed craters and pipe it like a second atmosphere, to print magnetospheres around fragile worlds with loops of current hung in the sky. They would learn to treat comets as livestock, herded inward from what remains of the outskirts, or cultivated in situ by outgassing black rock. They would also learn to read the large-scale barometer, not just the orbit around a star, but the orbit of a star around a galaxy that has grown tails. Worlds become deserts under a redder sky because supply chains broke. Supply chains can be rebuilt, locally and temporarily, by minds that understand both chemistry and weather that stretches between galaxies. A fossil shoreline is a warning, but it is also a ruler. It measures what was lost and what must be replaced if seas are to return. Over longer arcs of time, the morphology finishes the sentence the environment began. What started as a blue spiral with gas-rich arms becomes a smoother, lensy disk, the kind astronomers file as an S0, its star formation rate dialed down to a whisper while old giants dominate the light. The criterion that decided its fate was simple and brutal. When the headwind's ram pressure exceeded the galaxy's anchoring gravity per unit area, layers of the interstellar medium could no longer stay bound. The threshold was crossed first in the outskirts, then marched inward as orbits carried the disk through denser, hotter lanes of the cluster. Pre-processing in groups often primed the victim before it ever met the main storm. Harassment, tides, and starvation had already thinned the pantry, so the tentacles were as much diagnosis as outcome. In the wake, dust grains charged by ultraviolet light and plasma impacts struggled to survive. Sputtering lifetimes shortened, coagulation stalled, and what remained was lofted into the intracluster light as a cinnamon haze that reddened the space between galaxies. The central engine was not a bystander. As residual gas funneled inward under torques and pressure gradients, accretion switched on in fits and starts, and each episode sent out cones of hard photons and, sometimes, narrow jets. Those lanterns cut through the already rarefied medium and set chemical clocks in planetary skies. Methane fell under relentless photolysis. Nitrous oxide was whittled away faster than biology could plausibly replace in a thin-air world. Chlorine chemistry, fed by evaporites and perchlorates, produced hazes that raised albedos and cooled surfaces even as the greenhouse shifted from water to carbon dioxide. As oxygen accumulated not as a breath but as an echo of lost hydrogen, O2 collision pairs etched dimer features into transmission spectra. False positives for life multiplied in a neighborhood predisposed to dryness. Geology pivoted to wind. With hydrology retiring, Aeolian physics wrote the landscapes, saltating grains carved yardongs from friable rock, dunes migrated in broad, low-slung rivers of sand, electrical double layers built along dust plumes, and discharges stitched the skies with dry lightning that manufactured nitrates without rain to wash them to sea. Silicate weathering slowed until it became a boundary layer phenomenon in rare fogs over briny pans. Carbonate platforms, once buffers in a lively carbon cycle, stood exposed as monuments to the time when acid-base chemistry had a partner in precipitation. Isotopes kept the ledger, D/H ratios in any remaining waters trend high, 38 AR/36 AR drifts upward, and noble gases grow fractionated as the lightest isotopes find the escape hatch first. In drill cores on such planets, if anyone ever collects them, fluid inclusions would bracket the retreat of the seas with heartbreaking precision, salinity climbing, redox potential shifting, sulfates and chlorides asserting themselves where once there had been carbonates and clays. The diversity of outcomes still mattered. High-gravity super-Earths held on to dense atmospheres that pressed deserts beneath kilometers of air, moving heat efficiently but unable to return water once it had been photolyzed and bled away. Mini-Neptunes, especially those close to their suns, shed their envelopes faster under elevated EUV, stepping down toward rocky cores that inherit whatever volatiles were left in their mantles. Tidally locked worlds around cool stars became two-tone planets, copper daylight hemispheres under permanent dust canopies and nightsides where permafrost survived in shadowed basins, fed by faint vapor transport across the terminator. Icy moons, battered on the surface by sputtering and micrometeoroids, retreated into themselves. Brine oceans persisted beneath thick lids, warmed by radiogenic decay and tidal flexing, a stubborn chemistry class continuing after the school above closed. Rogue planets, shaken loose by cluster tides and close passages, drifted into the intracluster medium where whatever air they carried would condense and freeze unless they were wrapped in deep hydrogen blankets that could trap geothermal heat. The cluster did not only make deserts, it curated a cabinet of extreme habitats whose common trait was thrift. From an observatory's standpoint, the signal became a demographic gradient more than a single spectacular case study. In regions where jellyfish tails gleamed, exoplanet surveys would find suppressed water features across many temperate candidates and a bias toward thin or oxidized atmospheres. Phase curves with sharp day-night contrasts would outnumber those with gentle slopes. Albedo maps would show continents that were too bright for too long. Spectra would lean into CO2 at 4.3 micrometers and 15 micrometers, show enhanced O4 around 0.63, 1.06, and 1.27 micrometers, and display sulfur aerosols whose broad blue to UV scattering signatures hinted at volcanism working with dry air. Helium at 1083 nanometers would flare in escaping envelopes, and sodium and potassium lines would fluctuate under variable ionization from passing through hard radiation cones. Polarimetry would find telltale forward scattering peaks from fine dust, and time domain measurements would catch global dust seasons that rose and collapsed on chaotic schedules set by storm physics rather than monsoons. If, despite all this, life appeared early enough, it would adapt its metabolism to scarcity and to oxidants. Phototrophs, if they ever existed on the surface, would retreat underground or into endolithic niches, leaving pigments that peak not at ocean-friendly wavelengths but where dust and thin air still let photons through. Chemotrophs would haunt brine pockets and evaporite margins, cycling halogens and sulfur in tight loops. The biosphere's footprint in the atmosphere would be small and twitchy, hard to catch, easy to confuse with abiotic production, yet locally decisive. The lesson for a searching telescope would be methodological humility. In harsh neighborhoods, life, deserts, and false positives rhyme, so the diagnosis must be made with ensembles, with context maps of radiation, with cross-correlations between galactic weather and planetary spectra. There is, however, a coda to the stripping story. Orbits do not always dive forever, some galaxies bounce. Backsplash trajectories carry gas-poor disks back toward the outskirts where the intracluster medium thins and the headwind slackens. If filaments feeding the cluster remain accessible and if the halo has not been completely scoured, trickles of cold gas can rain back through thermal instabilities, condensing where turbulence seeds density peaks. Rejuvenation is rarely dramatic, but it is not fiction. Rings of star formation can light briefly in systems that have been filed as retired. On planetary scales, that doesn't refill oceans, but it can modestly re-wet skies where mantle outgassing continues and cometary fragments still graze the inner system. The grand desert is not perfectly permanent, it just has inertia. Against that inertia, technologies could act as local weather, mirrors in orbit to push climate equilibria, electromagnetic shields to fatten magnetospheres, pipelines from cold traps and crater shadows to valley floors, comet farms tended in the dim outskirts and steered inward like rain on schedule. In a place where a galaxy once grew tentacles and shed its lifeblood into the wind, the difference between a fossil shoreline and a living sea may eventually be the will and patience to reverse, at small scales, the physics that made deserts at large ones. In numbers the rule is plain. When the headwind's pressure ICM v superscript 2 overtakes the restoring force per unit area, roughly 2 pi g sigma star operator gas, layers lift and flow. Cluster cores offer ICM of 1010 superscript 3 cm superscript 3, temperatures of 1010 K, and orbital speeds near 1000 to 2000 km s superscript 1. The product is enough to unbutton a disk in tens to hundreds of mir, leaving filaments that can stretch 50 to 100 kiloparsecs before they fade. In those wakes, magnetic draping raises the alphane speed and stabilizes some surfaces while others shred. Effective viscosity is debated but never irrelevant. Turbulence seeds cold clumps that briefly defy evaporation. A few knots turn into compact, fast-moving fireballs of stars that will orbit as orphans when the gas is gone. What looks like ornamental streamers is a conveyor belt of supply lines being carried into the void. For planets, the timeline is staggered. Atmospheres respond on photochemical and escape timescales, years to megayears, long before continents can answer. Energy-limited escape rates scale with EUV flux and planetary radius over mass. Add non-thermal channels under compressed magnetospheres and the ledger tilts further. Helium 1083 nanometers absorption deepens in outflowing coronas, sodium and potassium lines jitter with ionization fronts, water vapor bands flatten when the hydrological engine starves. A world that once showed rotating glints from seas develops light curves dominated by dust opacity and albedo swings. Phase curves sharpen into steep day-night contrasts as thin air and dust curtains decouple hemispheres. If you stack spectra for dozens of temperate candidates in a jellyfish's neighborhood, you read the same chorus: CO2 steady and strong, O2 dimers too prominent for comfort, H2O muted, sulfur aerosols broadening the blue. It is a population signal of deserts written by a galactic wind. Dust becomes the author of landscapes and skies. Grain charging under UV and plasma sets the sign and magnitude of electrostatic forces, controlling saltation thresholds and lofting efficiencies. Once aloft, fines raise the effective planetary albedo while cooling the ground, but they also warm the air if absorption is strong. The vertical temperature profile tips toward inversions that cap convection. Lightning grows from friction and double layers rather than moist updrafts. Nitrates accumulate without rain, a surface fertilizer with no farmer. Silicate weathering, the slow thermostat of climate, contracts to rare fog events, confined to cold traps and valley bottoms where brines can briefly wick and react. Carbonate and clay assemblages freeze a chronology. Early layers rich in hydrated minerals and low D/H give way upward to sulfates, perchlorates, and heavy water signatures. Noble gases fractionate as the escape valve preferentially admits the lightest isotopes. Even without fossils, the rock remembers the retreat. Not all atmospheres thin, some thicken into pressure deserts. Super-Earths hang on to heavy, dry skins that move heat efficiently but cannot resurrect oceans once hydrogen is gone. Their skies become CO2-rich with trace CO, O2, and O3 set by photochemistry, and clouds, where they exist, are sulfate hazes or lofted dust rather than water. Mini-Neptunes near their stars slide down the mass radius plane as cluster-enhanced EUV trims their envelopes, some halt as hot, dense rocks with residual steam in their mantles, others as iron-heavy remnants that glow dull red at dusk. Around cool dwarfs, tidally locked planets grow copper daylight hemispheres under permanent dust veils and nightsides that hoard ice in shadowed basins. Cold, dense air spills downslope as katabatic winds that sculpt dunes into amphitheaters. Icy moons fare best in silence, sputtering skins above, brine oceans below, chemistry warmed by radionuclides and tidal strains, a private weather powered by geology rather than sky. The host's nucleus, when it wakes, draws lines across these fates. Ionization cones and jets carve hard-edged sectors where EUV and particles spike by orders of magnitude. Planetary systems that drift through those beams during a pericenter epoch endure punctuated losses. Helium tails brighten, ozone columns wobble, and upper atmospheres acquire hot layers that speed escape. Outside the cones the milieu remains harsh but steadier, inside, it is a kiln. Over an orbital gigayear, a star can sample both regimes several times, writing alternating stripes of loss in any surviving climate archive. On the scale of a cluster map, you can cross-correlate AGN duty cycles with waterband suppression in exoplanet ensembles and recover a weather chart whose isobars are radiation fields. Simulations close the loop. Cosmological MHD runs of clusters resolve RAM pressure, draping, and multiphase condensation. Embedded galaxy models track the gun.criterion radius marching inward. Nested climate models translate external fluxes and particle spectra into escape rates and dust season statistics. Feed those into forward models of spectra and light curves, and you get predictions you can actually compare, the fraction of temperate planets with water bands below a threshold as a function of cluster-centric distance, the distribution of helium line depths near jellyfish wakes, the polarimetric slope as a tracer of fine dust on worlds near strip tails. The hypothesis becomes testable not with a single poster child but with demographics. There are edge cases that complicate the picture in instructive ways. Backsplash galaxies that have already been stripped once can drift back to the outskirts. If their halos still seed thermal instabilities, drizzle of cold gas can restart star formation in rings or lenses. That is too little to refill oceans, but it can fatten thin skies where volcanic outgassing continues. Group infall preprocesses some victims so severely that by the time they meet the main headwind there is little left to strip, deserts by inertia as much as by weather. Conversely, a massive, compact disk with high sigma star operator can keep its inner gas longer, feeding an AGN that intermittently overpressurizes the remaining ISM and drives outflows in directions the wind had not chosen, a crosswind within the wind. Planetary outcomes mirror this variability: rare refugia under thick air, caves with brines beneath evaporite caps, crater shadows that collect frost each winter and briefly run rivulets under a thin sun. If mines arise before the hydrological clock hits zero, engineering can bend the curves locally. Electromagnetic shields stationed upstream can swell magnetospheres and cut particle-driven loss. Sunshades and mirrors can push radiative equilibria back toward condensation. Ablative dust launched during peak storm seasons can break feedback loops by seeding larger grains that settle faster. Volatiles reimport from cold traps, crater shadows, and remnant comets can be plumbed like a second atmosphere, circulated through closed basins to restart a minimal water cycle. The energy budget is demanding but not absurd for a civilization that has already learned to live with dust. The hardest lesson is scale, the same physics that quenched a galaxy stars a planet, so solutions must respect both the small and the large weather, the teleconnections from cluster shocks to dune crests. From a distance the story reduces to a simple equivalence: jellyfish galaxies are supply chains snapping in public, desert planets are the invoices stamped, insufficient funds. Tales are not just pretty, they are receipts fluttering in a hot wind, itemizing what was carried away. Read enough of them, and you can predict the color of dunes under alien suns, the chemistry of thin skies, the odds that a transmission spectrum's oxygen is breath or echo. And if you ever walk across one of those shores where waves no longer come, the polygon cracks and salt crystals under your boots will be telling the same tale the cluster told, that gravity, pressure, radiation, and time can remake a blue world into a memory, and that memory, in rock and light, is precise enough to navigate by. When supply collapses, even color changes. Skies over desiccating worlds turn butterscotch near noon and copper at dusk as submicron silicates take over the scattering budget and push blue light out of the air. The horizon glows longer because dust holds sunlight after the star has set, yet the twilight is mute because aerosols suppress the rainbow signatures that water once made. Daytime convection grows tall, not wet. Columns of hot, dusty air rise like chimneys, capped by inversions that trap heat aloft and leave the ground oddly cool until the sun steepens. Dust devils stitch black lines across dry pans, their cores electrified by triboelectric charging that builds double layers and throws miniature bolts into the haze. Yardongs, wind-carved fins, lean in the prevailing direction like frozen flags. Where brines briefly emerge, they crawl rather than flow, advancing with capillary fingers through salt crusts that crunch underfoot and preserve footprints for years. The chemistry of such places is not quiet, it is busy at low tide. Perchlorates, sulfates, and nitrates trade oxygen, iron flips valence in thin films, volcanic glass hydrates just enough to record humidity cycles and then dehydrates again, clocking seasons that have no rain. Deep below, water is not gone so much as collateralized. It sits in crystal lattices as hydroxyls, bound in clays and serpentinites, locked behind activation energies that only metamorphism or volcanism will pay. Mantle outgassing continues on planets with warm interiors, but what climbs is a thin stipend, not a salary. CO2 and SO2 in puffs, trace H2 and H2O that frost the night before photolysis can promote them. Basaltic plains disgorge darker sheets that cool under a dust fall before they can weather to the reds and ochres above, creating spectral two-tone terrains whose albedo jumps are large enough to modulate unresolved light curves. In caves, chemistry holds on longer. Drip points under cap rocks feed stalactites of halite and thenardite instead of calcite, inclusions trap bubbles whose gases will one day read like a cardiogram of the dying sky, oxygen rising, hydrogen vanishing, noble gases fractionating in slow, elegant arcs. Microbes, if present, would write their signatures as isotopic biases in sulfur and nitrogen along evaporite margins, faint against the louder signal of photochemistry but still legible where energy is steady and ultraviolet light is thin. Across the cluster the same motifs repeat with local accents. In outskirts where densities are lower, stripping is partial and strangulation dominates, star formation fades by starvation rather than by shock, so planetary climates decline more slowly, with lingering lakes that turn to salt steppes over tens of millions of years. In intermediate radii, pre-processed galaxies fall in with their pantries already half empty, their tails are shorter, their deserts more advanced. Near the core, full jellyfish flourish and then wither, there the statistics are starkest, more quenched disks, more thin airs, more oxidized skies. The central engines choreograph the exceptions. When an accreting nucleus flares, a pencil of hard light traces a corridor of exaggerated loss. When it sleeps, planetary erosion returns to the dull arithmetic of mean fluxes and compressed astrospheres. Over a gigayear a solar system may traverse cones and shadows several times, and a desert planet's rock will remember the cadence as bands of chemistry layered like pages. Observationally, the test is a census rather than a portrait. Take temperate planets in projection against a stripped wake and stack their spectra. Water bands should weaken relative to CO2 and O4, and helium at 1083 nanometers should deepen for close-in subneptunes. Sort by cluster-centric distance and the dryness should ease with radius. Cross-match with tracers of recent stripping, H-alpha beads and tails, truncated gas disks, hard UV fields, and the bias toward dust-dominated phase curves and strong day-night contrasts should sharpen. Polarimetry ought to find steeper blue slopes where fine dust rules. Time domain data should catch storm seasons that ignore orbital phase and obey dusty feedbacks instead. Direct imaging with next-generation coronagraphs will map continents that are too steady and too bright, lacking the specular hints that seas scatter. None of these signals alone convicts a world of being a desert by cluster weather, but together, mapped onto the galaxy's own scars, they make a verdict. There are countercurrents worth savoring. Gas fountains from halos that were not fully erased can condense as thermal rain and briefly repaint rings with star formation, softening radiation fields and dribbling fresh comets inward. Giant planets, if present, can serve as volatile accountants, shepherding what remains of an outer belt, swapping angular momentum to flick water-rich bodies sunward on schedules civilization could exploit. Tidally heated moons keep oceans under ice even as their skies sandblast away. Rogue planets shaken loose by tides become cold archives where atmospheres collapse as snows and keep, in layered ices, a chemical history more faithful than any weathered rock. Even dust can become an ally. Engineered lofting of larger grains during peak storm seasons can push microphysics toward faster settling and clear windows for light and warmth to reach ground. From a surface, the phenomenology is intimate. Noon light has weight, it presses without heat when dust aloft inverts the lapse rate. Shadows are soft-edged, the sun's disk pales to a brass coin long before it sets, the stars come late and weak. A storm announces itself not with thunderheads but with a slow loss of distance as the world turns sepia. Static prickles on skin because the air is poor at discharging, nearby rocks tick with tiny sparks in the dark. If mountains exist, they wear aprons of dunes that creep uphill in rare, violent gusts and slide down in long, sighing avalanches. In the lee of any obstacle, you find a lens of fines, silky and treacherous. Underfoot, crust breaks into polygon plates with rims white from salts that have wicked upward and crystallized. Your breath would taste metal if you could breathe it at all, instruments would foul, optics would film, filters would clog and then tear, yet chemistry kits would be happy, because the air is honest about what it has lost. On the scale of galactic evolution, jellyfish episodes are punctuation marks in long sentences about supply chains. Filaments that once poured cold gas along cosmic scaffolding into halos find their way interrupted by hot atmospheres and crowding neighbors. The grammar shifts from clauses about growth to ones about allocation. The planets inside those sentences inherit the edit. Where supply is steady, climates can meander and recover. Where it is cut, they ratchet toward aridity with only small backsteps allowed by volcanism and luck. Read enough spectra, and you can tell which paragraph a world belongs to without seeing the galaxy at all. Read the galaxy, and you can guess, within odds, the color of its planet's dunes. If intelligence emerges early in that arc, the survival manual will read like a weather book. Build shields upstream in plasma, not only shade downstream in light. Treat comets as reservoirs, not events. Pipe volatiles the way rivers once did, turn crater shadows into cisterns and valley floors into closed basins with recycled skies under transparent roofs. Fold dust into architecture instead of fighting it, use it for radiation mass, for thermal lag, for controlled scattering that lengthens day when needed and shortens it when not. Calibrate expectations to teleconnections that run from cluster shocks to your barometer. Understand that deserts are not only endings but platforms, stable, predictable, stingy but generous in sunlight, manageable once their feedbacks are domesticated. On such worlds the horizon is not a line where water meets sky, it is a ledger, and every dune crest is an entry that balances gravity, pressure, and time. Eventually the deserts begin to inherit the stars. When a galaxy sheds its gas, the asymptotic giants it already minted take their turn as weather makers. Slow winds from bloated elders bleed carbon dust, silicates, and S-process crumbs into an environment that can no longer turn those gifts into clouds. The grains drift as free agents, not seeds for rain. They redden starlight along tangents and lay thin, photochemically active films on exposed rocks, catalyzing halogen cycles in sunlight that is now harder, more ultraviolet than the skies their ancestors knew. Micrometeoroid fluxes rise as cluster tides and harassment stir loose debris. The thin air offers little break, so small impacts become hot pinpricks that weld glassy skins onto dunes and melt dark varnishes on bedrock. Over thousands of seasons the upper centimeters of regolith evolve into a laminated archive of sparks and dust, each layer a tally of storms, impacts, and chemistry accomplished without rivers. Climate models for these worlds converge on a few attractors. With little water to set a moist adiabat, lapse rates skew toward dry limits, inversions and dust layers decouple the boundary layer from free air, the diurnal cycle is governed by radiative time constants of aerosols rather than by latent heat. Albedo, dust feedbacks carve two basins of behavior, bright, thin air states with strong day, night contrasts and deep, dust-loaded states where the sky glows and the surface cools, a kind of anti-greenhouse that stalls convection while keeping the middle atmosphere warm. Transitions between them are triggered by thresholds in wind stress and particle size distributions, so the timing is chaotic, with multi-year plateaus punctuated by abrupt flips. If oceans ever existed, the shoreline fossilizes as a reflective ring that modulates planetary light curves. Spectroscopy of those rims would show evaporite suites ranked by solubility, carbonates low, then sulfates, then chlorides, while the isotopes climb like stair treads, D/H high, (18O/16O enriched, noble gases stripped in mass order. Photochemistry rewrites the palette. With water lines faint, CO2 becomes the dominant infrared narrator, its 4.3 and 15 micrometers bands deep and squared off by pressure. Oxygen dimers mark the visible and near-infrared at 0.63, 1.06, and 1.27 micrometers, but the triad is a memorial, not a breath. Ozone appears in a precarious column that swells under strong UV only to be cored by particle events. Sulfur oxides fed by volcanism and dry lightning seed aerosols with wide, blue-sloping scattering that steals contrast from reflected light maps. Trace CO lingers because nothing wet remains to finish oxidation. Nitric acid forms on dust and waits for a rain that never comes. Where chlorine finds perchlorates in sunlit films, it cycles with oxygen in reactions that proceed in salty brines for minutes at dawn and freeze into silence by noon. If biology ever touched this chemistry, its signatures would be subtle, fractionations in sulfur around evaporite margins, organics trapped in halide like tiny time capsules, signals that survive only because the environment is so still. The neighborhoods that birth jellyfish are not uniform wind tunnels, they are patchworks of fronts and relic shocks, mini halos and cavities inflated by old radio lobes. A solar system's path through this quilt changes the punctuation of loss. Cross a cold front and the ram pressure can double, step into an ionization cone and particles spike by a factor of 10, slide into a shadowed eddy behind a subcluster and the environment softens for a few million years. Over one galactic year the cumulative exposure matters more than any one squall, yet rocks remember squalls, glass spherules aligned with a wind that blew for a century, nitrate spikes layered between dust beds, a band where helium escape heated the exobase and etched its signature into the helium triplet that a telescope, centuries later, will read as a flare in a transit light curve. Giant planets modulate fate like valves in a pipe. A massive neighbor can corral what remains of an outer belt into resonances that drip water-rich bodies inward on long, predictable periods. It can also eject them wholesale when the stellar neighborhood jostles, trading a drizzle for a drought. Where belts survive in shards, bombardment delivers pulses of heat and trace volatiles that briefly sag dust feedbacks and carve dark streaks after storms, then vanish back into the thin air. Tidally heated moons, meanwhile, keep private weather under ice, circulating brines with minerals that encode pressure, temperature, and radiation as cleanly as any atmosphere. In caves and fractures, chemistries learned from Earth's Atacama and Antarctic dry valleys would hold out, perchlorate reducers, sulfur cyclers, organisms that treat humidity like a harvest and sleep until it returns. From a telescope seat the program is straightforward and grand. Map jellyfish tails and hard radiation fields across clusters, sort transiting planets by projected position along those scars, stack spectra with care. Expect helium 1083 nanometers absorption to deepen near strong EUV corridors for close-in sub-Neptunes. Expect O4 to correlate with suppressed H2O in temperate candidates projected against wakes. Expect polarimetric slopes to steepen where fine dust rules. Watch phase curves for dust season hysteresis, not orbital phase coherence. Look for continents that are too steady and for the missing knife-edge glint of seas. Use millimeter eyes to weigh dust in exospheres and wakes. Use X-ray maps to chart the headwinds. Fold it all into a joint inference that treats galaxies and planets as one weather system. None of this renders hope quaint. Scarcity is a design prompt. On a dry world a civilization would edit the radiative budget with mirrors and veils, not just shades. It would swell magnetospheres upstream with current loops, not only huddle beneath domes. It would treat comets as cisterns and crater shadows as reservoirs, piping volatiles through buried conduits to closed basins roofed by transparent films that hold the local sky at a few tens of millibars. It would time dust with seeding, launching larger grains during peak storm thresholds to bias microphysics toward fast settling in open windows for agriculture that drinks from recycled brines. It would use the thin air as mass for radiation shielding and thermal lag in architecture, walls that glow at dusk because they have stored the day. Most of all it would read teleconnections, learning to forecast not just its stars' moods but the clusters, and to schedule life against shocks it cannot soften. In the end the analogy remains tight. A galaxy that grew streamers under pressure is a ledger of supply interrupted. A planet that turned to desert is that ledger paid in local currency. The same inequality, external force over internal hold, drives gas from disks and water from skies. Where the quotient dips below unity, tails retract and rains might return in trickles. Where it climbs, the streamers lengthen and dunes advance. The science is an equation, the vista is a copper horizon under a redder sun. The lesson is practical. Climate, at any scale, is logistics, and logistics can be mapped, predicted, sometimes repaired. Read the tentacles, and you read the fate of seas. There is a second ledger written not in light but in spin. Dust and rock grains tumbling through thin air align with magnetic fields that thread both the planetary boundary layer and the larger intracluster wind. Their preferred orientations polarize scattered sunlight and inscribe a weak, rotating signature that follows the field more than the weather. Over seasons the pattern drifts as the heliospheric nose presses under external pressure. Over millennia it wobbles with the star's motion through patches of denser plasma. A remote observer reading those polarization angles against time could back out the geometry of both the planet's field and the headwind that squeezes it, an inverse barometer from glints. In the subsurface, remnant magnetization captures storm epochs as stripes, Dust-laden gust fronts carry charged fines that settle into layers whose magnetic textures differ from calm air deposits. Drill a core and you would hold a barcode of wind and field, a palimpsest where every stripe is a gust and every reversal a squall written by plasma far beyond the sky. The mechanics of loss also change with altitude in ways that matter for spectra. In rarefied, oxidizing atmospheres the homopause sinks, molecular weights stratify earlier, eddy diffusion weakens while molecular diffusion takes over, letting light species climb with fewer collisions. Exospheres fatten and adopt comet-like geometries, especially around small planets with hot day sites. Helium becomes the storyteller because it is both abundant in the mantle and honest about heating. The metastable triplet at 1083 nanometers deepens when EUV is high and magnetospheric compression opens particle routes. Hydrogen, when present at all, paints Lyman alpha wings that telescopes must peel from the interstellar foreground. Deuterium tells you the history of escape if you can catch it. Oxygen does not merely remain, it polymerizes into O2 collision pairs and feeds an ozone layer whose thickness jitters with particle weather, a flicker you can time against the heartbeat of an active nucleus or a passage through a cluster cold front. Geography builds its own statistics. Without rainfall to erase relief, dunes and yardongs inherit prevailing winds and preserve them as macro-scale compasses. On basin floors, evaporite polygons grow to hundreds of meters across, their edges heightened by capillary wicking that lifts brines and leaves salts at rims. In thermal IR those rims glow at dusk because crystals hold heat longer than dust. In reflected light they redden and brighten the landscape enough to write shallow, broad features into disintegrated phase curves. Over lava plains, thin films of desert varnish mature under UV and dust, darkening spectra in the red and near IR without the water-related absorptions that biogenic varnishes on wetter worlds would show. Where volcanism continues, gases erupt into thin skies and condense as exotic frosts. SO2 turns to bright hoarfrost in crater shadows only to sublimate by noon, an albedo transient large enough to modulate the light curve for days. Each process is a punctuation mark a telescope can hear if it listens long. Galaxies add their cadence. Subcluster mergers launch sound waves and shocks that ring the intracluster medium. As those arcs pass, the headwind's density, temperature, and bulk speed all change at once. A star system that happens to be near pericenter when a shock arrives experiences a compounded season, RAM pressure peaks, EUV fields harden, and particle backgrounds spike. Transit spectra taken during such episodes would show an atmosphere in a breathing mode, helium lines deep, sodium absent, water flat, before relaxing toward its baseline. Stack many systems by position angle around a jellyfish wake and the variability should synchronize with X-ray surface brightness edges and radio relics. It is multi-messenger climatology. Use X-rays to see the wind, radio to see the fossil lobes and draping fields, optical/IR to see the deserts that wind and fields create. There are chemical tricks that make deserts look briefly wet from a distance. Brine films in morning shade can grow microns thick and survive minutes before evaporating. They deepen faint absorption near 3 micrometers and add a whisper at 6 micrometers that could be mistaken for water vapor if time averaged. Chlorine chemistry builds perchlorates that, when illuminated, release oxygen and trace chlorine oxides, confusing ozone retrievals unless spectra are taken at multiple phases and tracked for particle events. CO lingers alongside O2 because the usual wet oxidation partners are missing. Interpret O2 plus CO together without context and you might claim metabolism. The antidote is ensemble context. Worlds projected against fresh tails should bias dry, those beyond the caustics of ionization cones should wobble less, those in backswirls behind subclusters should show slower loss and weaker O4. No single spectrum suffices, the paragraph matters. Buried waters and gases complicate the surface's finality. Serpentinization in ultramafic rocks keeps hydrogen trickling where heat and fractures allow, and with it a chemistry that can knit organics out of CO2 even when skies are thin. Clathrates archive past atmospheres under permafrost lids, thaw lines, if geology or impacts breach them, can exhale bursts of methane into air that is otherwise poor in reducing gases. Those puffs write transient signatures at 3.3 micrometers and in millimeter bands. They fade quickly under UV but recur with seasons of geologic stress rather than solar illumination. In caves, even thin humidity cycles leave concretions of halite and thenardite that grow like hour markers, trapping organics and noble gases in inclusions. If anyone someday reads them, the inclusions will recount the atmosphere's retreat in fluent isotopes and the pulse of particle weather as argon ratios and neon fractionation. Engineering, if it appears, would aim where physics least resists. Particles shielding upstream, current loops and plasma sails positioned sunward, changes ion pickup rates more efficiently than thickening domes can change photolysis below. Radiative editing uses angled mirrors to bias the diurnal cycle, lengthening gentle mornings when brines can be useful and compressing harsh noons when dust feedbacks run away. Microphysical tuning seeds larger grains ahead of storm thresholds to hasten settling and break the positive loop between lofted fines and atmospheric heating. Logistics reimports volatiles from cold traps and dark craters as if piping a second atmosphere through the crust, closing water loops inside roofed basins held at tens to hundreds of millibars, pressure enough for liquid, low enough to keep structures light. The greatest expense is knowledge, forecasting teleconnections from cluster shocks to local barometers well enough to plan agriculture, travel, and maintenance cycles in a sky that answers to two weathers. Time does not stop simply because rain does. Red giants fade, white dwarfs inherit neighborhoods that their progenitors helped desiccate, planetary systems settle into long afternoons under cooler suns. Deserts stabilize into quasi-steady states where dust seasons flip between two attractors with low-frequency beats set by orbital precession and storm thresholds. If halos drizzle a little gas back into the galactic disk, the radiation field softens, and a planet with residual outgassing can thicken its air from threadbare to merely thin. If comet herds survive in resonances, late trains of impacts can write dark streaks across bright evaporite rings and briefly push climates across condensation points inside domes. None of this rebuilds oceans by itself, but it shifts odds and lengthens patience, the two currencies that matter after supply chains have been cut. From such a world the sky at night is still an education. Jellyfish streamers hang as ghostly highways where new clusters twinkle, a reminder that even as one place starves another feasts. The constellations shift with the galaxy's slow bounce through the cluster's lanes, radio auroras crackle along magnetospheric ovals tightened by the wind, meteors are frequent and shallow because the air is thin, leaving more glass than ash. A traveler who knows how to read light would see, in every copper sunset and long twilight, the arithmetic that tied a galaxy's tentacles to a planet's dunes. A telescope that knows how to average would see, in every stacked spectrum, that same arithmetic written across dozens of worlds. And a civilization that learns the lesson would treat climate as logistics from the start, budgeting not only heat and light but also the quieter currencies of shielding, grain size, and patience, so that when the headwind rises and the pantry runs low, the ledger still balances long enough for seeds to take in a place where rain no longer comes. Instrumentally, the cleanest discriminants live where environments couple. Low-frequency radio should catch cyclotron, maser emission from magnetospheres squeezed by high external pressure, the cutoff tracks the planet's field strength, and the burst rate rises when solar wind proxies spike, so a cluster headwind that compresses astrospheres should brighten exo-auroras into the tens to hundreds of MJY at tens of megahertz for the most favorable hot, fast rotators. Millimeter spectroscopy can weigh dust in exospheres and wakes, with continuum bumps at 0.8 to 3 mm tracing micron, sub-micron grains lofted from dry soils. Cross-correlation with stellar radial velocity jitter separates planetary dust from stellar activity. High-resolution optical/IR transmission spectra resolve line cores to read winds and scale heights directly. Sodium D and potassium at 770 nanometers track ionization fronts, while the helium 1083 nanometers triplet maps energy deposition and outflow geometry with Doppler-resolved tails. Polarimetry constrains microphysics. A steep blue slope flags fine silicates, a flatter one suggests sulfates, and phase-dependent swings reveal particle growth after engineered seeding or natural coalescence. Stack all of this by cluster-centric distance and along X-ray edges and radio relics, and the ensemble resolves into an environmental sequence rather than a field star scatter plot. Dynamics adds another lever. Tides and flybys in crowded infall groups pump eccentricities and inclinations, imposing climate cycles that ride atop desiccation. Eccentric orbits push perihelion insolation spikes through thin skies that cannot buffer heat, yielding asymmetric phase curves and seasonal helium surges as exobases expand. Inclined orbits tilt dust circulation cells, biasing dune migration and building hemispheric albedo dichotomies that persist for millennia. Giant planets act as governors or saboteurs. Mild resonant migration can feed inward trickles of icy bodies on secular timescales, while close encounters can clear belts entirely, shutting down late-stage hydration. In the statistics, that means desert indicators should anti-correlate with stable long-period giants but correlate with systems showing hot Jupiter migration scars and eccentric inner architectures, a demographic fingerprint that large surveys can test. Laboratory and field work close the calibration loop. Beamlines and plasma chambers measure sputtering yields and triboelectric charging for analog dust under UV and particle fluxes matched to cluster cones. Thermal vacuum rigs quantify evaporation and salt crust growth rates in brines that last minutes at millibars. Flow tunnels in dry air map saltation thresholds as functions of grain size, charge, and pressure to feed GCM microphysics. On Earth, the Atacama, McMurdo Dry Valleys, and high Andes salas provide natural laboratories where perchlorate chemistry, nitrate deposition without rain, and halide inclusions preserve organics and noble gases in ways directly portable to retrieval models. Fold those constants into radiative, convective models coupled to escape physics, and the forward problem, spectra, light curves, polarimetry, lands in a region of parameter space narrow enough to invert for dryness with confidence once environmental priors from X-ray and radio maps are applied. Formation does not fully cease in stripped wakes, and that nuance matters. Star-forming beads along jellyfish tails host protoplanetary disks in harsher baths than typical H2 regions. Disk lifetimes shrink, outer radii truncate, and dust growth races against photoevaporation. The survivors skew toward compact, rocky systems with meager volatile budgets and early atmospheres pre-eroded by EUV, essentially pre-desert worlds. If any sub-Neptunes form, they do so late and close in, primed for rapid envelope loss that accelerates under cluster conditions. That production function predicts a higher fraction of bare, high-density planets near active tails, a shift observable through mass, radius statistics and helium demographics. Conversely, backsplash regions where halos drizzle a little gas back into disks soften the radiation field and widen the disk survival window, seeding modest rewetting by late comets and slightly thicker skies, a second-order effect, but one that should appear as a gentle radial gradient in waterband depth outside the core. Even the biochemistry of false positives sharpens with context. O2 alongside CO and a strong O4 triad, with muted H2O and variable O3 tied to particle weather, flags oxidation by loss rather than metabolism. Add perchlorate photochemistry and you get day-night oxygen flicker uncorrelated with seasons. A signature biology is unlikely to mimic at low pressure. Methane bursts that recur with tectonic stress or thaw lines but decay on photochemical timescales point to clathrates or serpentinization rather than cows. Sulfur isotopes near evaporite margins can bias by a few per mil in patterns opposite those expected from robust microbial cycling, and noble gas fractionation, 36 AR down, 38 AR up, anchors the escape history independent of chemistry. The solution is an observing strategy that is boring by design, multi-epoch, multi-band, cross-matched to environmental maps, patient enough to watch dust seasons flip and particle weather pulse, comparative enough to let ensembles speak where single worlds can deceive. If agency enters the scene, the easiest wins are upstream and microscopic. Plasma shield stations sunward to inflate magnetospheres cut ion pick up more for the same what than any dome could. Angled mirrors adjust local radiative budgets at dawn and dusk to lengthen the brief windows when brines are liquid. Grain-size engineering nudges storms toward faster settling, opening clear sky slots on schedules set by forecasts that ingest cluster shocks as boundary conditions. Logistics treats volatiles as infrastructure. Comet farms tended in resonant corrals, pipelines from crater shadows to roofed basins that hold a local sky at tens to hundreds of millibars, electrolysis and Sabatier loops running on sunlight that deserts generously supply. None of this rebuilds an ocean, but it stretches hydrological half-lives, stabilizes agriculture, and buys time, an honest currency in a place where a galaxy's tentacles once wrote, insufficient funds, across the sky. Detection can lean on background beacons as much as on the planets themselves. Place a bright quasar or cluster BCG behind a desert world and the tenuous exosphere becomes a foreground etching, narrow, time-variable absorption in Na-D, K, and metastable. He rides on the lamp spectrum as the planet's orbital motion Doppler shifts the lines through rest. Repeat the experiment along a jellyfish tail and the column densities should rise where EUV corridors harden, move off the wake and the signatures relax. Starlight occultations by thin, dusty halos, exospheres swollen by sputtering and micro-impacts, make shallow, chromatic dimmings that last longer than transits and recur with the planet's season rather than its period. Even without a transit, rotational mapping can find deserts indirectly. Stable, high-albedo continents and broad dust belts produce power at low spherical harmonics that refuses to decorrelate with time the way oceans do. Interiors keep a slow conversation with skies that no longer listen. Mantle oxidation states drift as hydrogen escapes and the crust warehouses oxygen. Outgassed species shift toward CO2, SO2, and CO, throttled by redox buffers rather than by rain. Basalts erupt into thin air and quench into glass whose hydration spikes only during rare, cool dawns. The glass then dehydrates, locking a humidity curve into mid-IR features that would look like weak shoulders near 3 micrometers to a patient telescope. Seismicity under low load produces dust fountains when fractures open, a coupling between tectonics and weather that writes episodic brightening into phase curves months after the quakes themselves. Where ultramafic rocks meet water in deep crustal pockets, serpentinization keeps hydrogen trickling upward. The trickle is small, but in thin air it is enough to paint fleeting methane flares that a spectrograph can catch if it is disciplined about cadence. Landscape evolution in these climates runs on thresholds. Once grain-size distributions tip below a critical diameter, saltation becomes self-sustaining. Dunes encroach on uplands and bury paleo-shorelines like pages interleaved into a thicker book. Yardungs carve along bedding plains until a single storm season under unusually high winds collapses entire fins and resets topography in a year rather than a millennium. Evaporite polygons, fed by capillary rise from brines meters below, coarsen as stress concentrates at rims. Crack patterns propagate like slow lightning across basins, creating kilometer-scale rings that store thermal inertia and act as passive timekeepers in thermal IR. The rare hydrologic pulses, impact melts, brief aquifer discharges after quakes, volcanic snowfalls on cold plateaus, leave overprinted chemistries in halos around vents and craters. Bullseyes a retrieval pipeline can learn to recognize as the fingerprints of accidents rather than climate. On galactic scales, the stopping time for star formation and the drawdown time for planetary water need not match, yet they rhyme. Disks quench over a few times 10 years as inflows are cut and reservoirs stripped. Planets pace the decline with photochemical loss. non-thermal escape, and the exhaustion of late volatile delivery. Infalling groups pre-process both ledgers, thinning gas and stirring orbits before the main cluster wind does its work. Backsplash orbits offer temporary reprieves, the headwind eases, AGN cones are crossed less frequently, and halos can drizzle cold clumps back onto anemic disks, conditions that soften radiation fields and lengthen atmospheric half-lives by factors of a few. The aggregate effect, measured with a large enough sample, should appear as a gentle outer rise in waterband incidence and a fall in O4 strength even before you leave the virial radius. Instrumentation earns its keep by being boring and relentless. Multi-epoch transmission spectra across dust seasons prevent brine film mirages from masquerading as humidity. High-resolution line profiles track outflow velocities and separate thermally driven escape from ion pickup by their Doppler shapes. Simultaneous X-ray and radio maps set priors on EUV and particle flux so retrievals do not hunt ghosts. Polarimetry at a handful of well-chosen phases distinguishes fine silicates from sulfates by slope alone. Thermal phase curves captured over years map the flips between the bright thin and dust-loaded attractors. Millimeter photometry weighs exospheres and sifts out planetary dust from stellar granulation via cross-correlation with radial velocity jitter. None of these data singly clinch dryness. Taken together, especially when stacked along jellyfish wakes and across cluster-centric annuli, they turn anecdotes into a climate atlas. If mines inhabit such latitudes, their engineering will look like weather control scaled to thrift. Plasma mirrors and current loop stations sunward swell magnetospheres and cut non-thermal loss by orders of magnitude with power budgets modest compared to doming continents. Heliostat arrays bias mornings longer and noons shorter inside roofed basins, stretching the liquid window for agriculture that drinks brines and returns them with minimal fractionation. Grain size management, seeding larger particles upwind before threshold winds arrive, short circuits runaway dust seasons and opens clear sky lanes on schedules tied to forecasts that ingest cluster shocks as boundary conditions. Logistics treats volatiles like infrastructure, comet corrals maintained in resonances, cryopipelines from crater shadows, electrolysis loops powered by a sun that deserts reflect generously. Oceans do not return, but half-lives lengthen, yields stabilize, and culture learns to read the teleconnections that made their skies stingy. There are edge signatures worth anticipating because they sharpen the story where it frays. Thin, oxygen-rich atmospheres with perchlorate chemistry can generate day-night O2 flicker uncorrelated with seasons, a behavior unlikely for photosynthesis and easy to flag with cadence. Sulfur aerosol loads that rise after particle events but not after temperature swings point to dry lightning and volcanism rather than biology. Noble gas ratios, 36 AR depleted relative to 38 AR, neon fractionated in mass order, anchor escape histories that photometry cannot fake. Stack these against a map of H-alpha beads in jellyfish tails, X-ray pressure jumps at cold fronts, and radio relics marking old shocks, and the ensemble coherence becomes difficult to explain with anything but weather that runs from kiloparsecs down to dune crests. Even the failures teach. A survey that finds no trend in waterband suppression with cluster-centric distance may be sampling backsplash populations that have already recovered some shielding. A null result in helium near strong EUV corridors could indicate widespread giant planet guardians that kept sub-Neptunes at bay, shifting the production function toward high-density worlds. Disagreements between polarimetric slopes and thermal phase curves may betray engineered grain size control rather than nature, an audacious but testable hypothesis if changes correlate with local calendars. The point is not merely prediction, it is diagnosis in the wild, with enough patience to let the environment reveal whether deserts are destiny or design. At night, under copper skies, the connection still feels visceral. The same inequality that pulled gas from a disk, external push over internal hold, etched polygon cracks at your feet and thinned the breath in your lungs. The tails that once shone like jellyfish across the cluster were not ornaments but receipts, itemizing losses that cascaded from galaxies to grains. Read them well enough and you can forecast the color of a horizon on a world you will never walk, infer the chemistry of an air you will never breathe, and decide, early, while there is still margin, whether to build shields, mirrors, cisterns, and patience. In that sense, a desert planet is not a failure state, it is a syllabus, and the class it teaches begins with logistics and ends, if its students are stubborn, with rain made to order beneath a local, human sky. Models that let the physics speak sort deserts into a few durable archetypes rather than a blur. Thin air deserts are the Mars analogues writ large, surface pressures below a few tens of millibars, strong day-night contrasts, dust that sets both color and climate, and escape dominated by particles and heating at the exobase. Pressure deserts sit on the other side of the valley, super-Earths with many bars of dry CO2 that move heat efficiently but cannot cycle water, where lapse rates hug the dry adiabat and clouds, when they exist, are sulfate hazes and lofted fines, not rainmakers. Anti-greenhouse deserts are sky-thick but light-poor, aerosol layers warm the middle atmosphere and cool the ground, locking convection and stretching twilight, the surface lives under a bright ceiling and a cold floor. Brine pocket deserts stitch local exceptions into an arid rule, capillary films at dawn, cave drip points, crater shadow hoarfrosts that briefly melt and refreeze, microclimates that do chemistry for minutes at a time and then go silent for weeks. Each archetype has spectral tells, thin air worlds sharpen thermal phase curves and flatten water bands, pressure deserts square off CO2 at 4.3 and 15 micrometers and grow conspicuous O4, anti-greenhouse states redden polarimetric slopes with fine sulfates, brine pocket planets whisper at 3 and 6 micrometers on a cadence set by dawn and shade. Star type nudges these families along different tracks. Around cool dwarfs, EUV is persistent and flare spiky, tidally locked geometries compress climate into a dayside kiln and a nightside freezer, with terminator bands that act as valves. Helium 1083 nanometers often dominates the leakage story there, and O3 is jittery because particle weather punches holes as fast as photochemistry can stitch them. F and G-type hosts give steadier UV but larger habitable zones. Planets run cooler at the same stellar flux and can preserve thicker skins longer if supply is not cut. K-dwarfs, long-lived and moderate in UV, are temperamentally kind but not sovereign. Put a K-dwarf system inside a jellyfish wake and the cluster still wins the argument by tightening astrospheres and hardening the background. The neat part is that these differences are testable in ensembles. At fixed cluster-centric distance, dryness indicators should relax in step from M to K to G/F, with caveats where AGN cones slice across the map. Inside multi-planet systems the desert does not arrive evenly. Inner small worlds hit escape thresholds first, subneptunes lose helium-rich coronas until their mass radius points slide into the rocky cloud. Outer terrestrials, if belts survive, hang on longer, especially if a giant shepherds icy rubble into slow inward drizzles. That architecture writes structure into observables, helium tails cluster at short periods, waterband suppression spreads outward with time, dust-driven albedo features decorrelate with orbital phase on inner planets but remain seasonal farther out. Machine learning classifiers trained on simulated retrievals already recover these gradients when fed spectra plus simple environmental priors, X-ray pressure, radio relic proximity. The moral is procedural: do not fit a planet in isolation when a whole family portrait is free for the taking. Timescales keep the ledger honest. Energy limited escape, M tilde operator eta pyr p3f EUV slash, GMPK, /dem /sim /eta /pi r underscore p caret 3f underscore /mathrm EUV / gm underscore pk, M tilde operator eta pyr p3f EUV / GMPK. Drains light envelopes in tens to hundreds of mir at cluster boosted EUV, non-thermal channels at a comparable tax when magnetospheres are squeezed. Aeolian reshaping of landscapes runs from hours, dust devils, saltation bursts, to KYR, dune migration, to mere, Yardang sculpting. Photochemical oxidation can flip redox balances in a few mere once hydrogen export outpaces supply. Volcanic outgassing paces out in 1010-year pulses modulated by tectonics and mantle water content. None of these clocks match perfectly, which is why deserts retain texture. A Yardang field can persist under a sky whose chemistry already turned the corner. A world can show helium loss long after its dunes found equilibrium. A brine signature can recur in caves centuries after the last open-air rain. The rock is a faithful witness. Crossbeds and climbing ripples give wind direction and variability statistics. Evaporite sequences rank solubilities, carbonates at the base, then sulfates, then chlorides, while isotope ladders, D/H, carat18O/16O, argon and neon pairs, record escape and exchange in mass order. Silica-rich desert varnish grows under UV and dust, darkening near IR slopes without borrowing water features that would betray biology. Impact glass hydrates on cold mornings and dehydrates by noon, riding humidity in mid-IR shoulders that recur with season and microclimate. Cave halides trap bubbles that archive noble gases and trace organics. Read across a depth profile and you reconstruct a century-scale cardiogram of a dying sky. Dynamo physics adds one more hinge. Thin or thick, an atmosphere still modulates core cooling by setting surface heat loss. Deserts, especially thin air ones, can hasten cooling and extend dynamo lifetimes, buying magnetospheric protection even as UV bakes the top of the air. Conversely, pressure deserts insulate. Cores cool slower, dynamos may persist longer still, but the atmosphere's mass loads pick up processes and changes which escape channel dominates. That feedback explains why some thin worlds keep radio-loud auroras while others of similar mass go quiet. Mantle heat, lithosphere thickness, and sky mass form a three-body problem whose solution space has islands of protection and seas of loss. The false wet problem becomes manageable once cadence enters the plan. Morning brine films deepen 3 micrometers absorption for minutes. Perchlorate photolysis toggles O2 and O3 on particle weather timescales. Methane from clathrate burps paints transient 3.3 micrometers features that fade in days. None of these correlate with orbital phase the way oceans and clouds do. A boring schedule, multi-epoch spectra across months, co-observed with X-ray/EUV proxies and radio maps of the wind, unmasks them. Stack by position along X-ray edges and radio relics, and the mirages cancel while climate remains. If agency intervenes, it will exploit the cheapest gradients. Upstream plasma loops that fatten magnetosphere's lower ion pickup with watts that domes could never match. Heliostat fields bias diurnal energy so dawns run longer, when capillary chemistry and agriculture are most forgiving, and noons shorter, grain size seeding before threshold winds flip a dust season from runaway to self-limiting. Comet corrals and cryopipelines turn reserves in shadow into weather on demand inside roofed basins held at tens to hundreds of millibars. Radiation mass is free in deserts, dust itself, so walls carry sunlight as heat into the night, smoothing extremes for crops that drink recycled brines. None of this conjures an ocean, but it stretches half-lives, and in logistics that is often the whole game. Zoom back to the jellyfish and the analogy tightens again. Tails are public receipts of broken supply chains, deserts are those receipts paid locally. Read the pressure jumps in X-ray maps, the relic arcs in radio, the beads of H-alpha along streamers, and you can forecast spectra, CO2 deep, H2O shy, O42 proud, helium restless. Read enough spectra against those maps and you can forecast landscapes, bright evaporite rings, dunes with steep forward scattering peaks, yardangs aligned with a wind whose direction you measured from a galaxy scale shock. The environment is continuous from kiloparsecs to centimeters. The diagnosis should be too. And if a traveler were to stand under such a sky, the lessons would feel practical rather than grand. Noon would arrive as a pale coin above a bright ceiling, shadows would blur, static would prickle in the air, dust would taste of iron and salt. Instruments would foul, but ledgers would fill, grain sizes logged, humidity spikes timed, noble gases bottled, spectra taken at dull, disciplined intervals that let the planet confess not in a single dramatic moment, but in the steady arithmetic of loss. The same arithmetic that pulled a galaxy's gas into streamers wrote polygon cracks into the mud at their feet. Learning to read one teaches you to predict the other, and, sometimes, to nudge both toward kinder numbers. A stellar city switches on when a straight, luminous bar digs its gravitational oars into the disk and begins to move angular momentum outward like a conveyor. Gas that once circled lazily now meets the bar's leading dust lanes as oblique shocks. It cools, compresses, and slips inward along curved streamers, gathering at resonances where orbital families change character. At a kiloparsec scale, a ring kindles, H2 knots ignite in sequence, then overlap into a running fire that traces the oval like embers on a fuse. Deeper in, between the inner Lindblad resonances, orbits rotate 90 degrees and the flow stalls just long enough for self-gravity to bite. Tumors Q dips, sheets fracture into filaments, filaments bead into clumps, and the clumps shear into hundreds of embryonic disks, quiet centrifuges where dust settles, pebbles drift, and the first kilometer scale bodies begin their bookkeeping. The bar is not decoration, it is a torque machine, and every parsec it pulls inward feeds both a central starburst and the slow assembly line of planets. You can almost read the physics in the image, a bright, rectangular spine, two offset, smoky lanes where shocks live, interior arcs of gas curling like river mouths toward a calm inner pool stippled by protodisks. This pump is not steady, it comes in breaths. When inflow peaks, feedback is fierce, winds, ionizing light, and supernovae drill chimneys through the ring and spray metals over the inner disk. It is a spectacular, hazardous hour, great for enriching solids and seeding magnetic fields, terrible for fragile atmospheres. Then the engines sag. After tens to a few 100 million years the radiation field softens, turbulence decays from supersonic to merely brisk, and the sound speed falls enough for thinner midplanes and stronger pressure bumps. Migration traps appear where dust back reacts on gas, snowlines sharpen, dead zones switch on in the cooler inner few astronomical units, reducing viscous stirring. This is the window the bar secretly builds, a lull after the blaze when disks are metal-rich and long-lived, but the sterilizing fireworks have moved on or upward. Around K and late G-type suns nested in the ring's aftermath, warm orbits stabilize, periods of a few tens to a few hundreds of days where water can persist if the atmosphere is not flayed. Giant planets, grown fast by pebble accretion in the metal-heavy outskirts, stall at pressure maxima instead of plowing inward, sparing the inner architectures. The probability of temperate survivor spikes not during the roar, but in the eddy that follows it. Meanwhile the bar evolves under its own labor. Each parcel of gas that loses angular momentum to dive inward hands that momentum to the bar and outer disk, and dynamical friction with the halo slows the pattern until resonances march outward. If inflow is copious, a compact central mass builds and begins to undermine the very orbit family that props the bar up, buckling thickens the spine, sometimes an inner, faster bar sprouts like a relay baton to carry gas the last few hundred parsecs. These cycles write a secular biography, torque, inflow, ring, burst, lull, renewal, each pass flattening metallicity gradients, carving new rings, and resetting the odds for calm climates. Even a mild black hole episode can be folded into the cadence, a short, dim accretion flicker when gas kisses the last resonant barrier, more nuisance than apocalypse for life if it is brief and off-axis. From far away the scene reads as cinema without neon, a barred disk blazing along its axis, two pale rivers of gas pouring inward, and a grainy inner commons where newborn systems glow in thermal reds and amber whites, hundreds of small, hot crescents etched against a darker floor. But under that spectacle runs a careful ledger. Bars are engines that exchange order for structure, they compress entropy into stars and sort solids into disks, they open and close habitability windows on 100-million-year dials. Call them pumps of life not because they guarantee it, but because they sculpt the only conditions under which it can quietly take root and keep its balance while the galaxy catches its breath. Watch the bar long enough and you see it teach the disk to breathe. Spiral arms latch onto its ends like sails, amplifying the bar's pull on the gas and feeding back a tide that keeps the pattern alive. At corotation, where stars orbit with the bar's speed, orbits crowd and then thin like traffic around an on-ramp. Outside, the bar hands energy to the arms and they carry it downrange. Inside, the bar steals energy and the gas surrenders height and radius. Oblique shocks along the leading lanes turn orbital elegance into heat and density, and chemistry follows suit. Carbon chains grow longer, ices flash to vapor and back again, and dust mantles acquire metal skins that make pebbles stickier the next time collisions try to grind them down. The inner ring that seems decorative in a postcard is actually a slow collider, a racetrack where clouds overtake, bump, and merge until they have no choice but to collapse. The sequence repeats, but never exactly. The bar precesses, the halo tug drifts the pattern speed, and every cycle leaves behind a slightly rounder center with a disky, rotation-supported bulge that remembers the bar even if the bar itself fades. Inside the newborn systems, the flow is just as directional. Pressure traps at snowlines and at the edges of low ionization dead zones act like one-way gates, catching millimeter grains and turning a thin dust soup into stripes of abundance. Streaming instabilities wake when solids pile high enough, and gravity finishes the job, knotting pebbles into planetesimals in a geological blink. In high-metallicity disks born from bar-fed gas, cores fatten quickly but the same pressure bumps that helped build them also stop their drift, holding would-be giants in check before they bulldoze the inner real estate. Magnetic fields, stretched by shear and threaded by newborn currents, braid the gas and seed weak winds that carry away just enough angular momentum to keep accretion smooth without shredding the midplane. The ultraviolet glare that once sterilized the ring now flickers from farther out, filtered by dust and chimneys, cosmic rays that spike during the burst decay with their short-lived sources, and ionization settles into a patchwork that favors layered, stable atmospheres over stripped, bare rock. The central engine, if one lights, tends to whisper rather than scream during the quiet turn. A modest, dusty accretion episode can illuminate the last few hundred parsecs and inflate a warm molecular wind that scours the cavity without punching a hole through the disk. It is an odd kindness, a nudge that clears the innermost gas reservoir before it can overfeed the next burst, buying the ring a longer, softer afterglow. In that afterglow, water delivery becomes choreography rather than chaos. Icy fragments from beyond the snowline are jarred into slow diffusion by bar-driven resonances. Weak, secular tugs sweep them inward over millions of orbits instead of hurling them in a single storm. Each impact writes a small, survivable chapter into an atmosphere's ledger, and escape speeds, now unthreatened by nearby giants, keep what is gained. Even failure carries information. Bars that grow too efficient build a central mass concentration that sabotages the very orbits that support them. The spine kinks, the pattern softens, and for a while the disk coasts on memory. Yet the outer disk, ripe with fresh asymmetries and a halo still willing to lend torque, can spawn a new bar that inherits the lanes and restarts the pump. Every rebirth rethreads metal through the inner few kiloparsecs and repaints the gradients that planets later mine. The clock for habitability windows is tied to these secular beats, a luminous season of compression and noise, a tempering season of assembly and cooling, and then a long, dim plateau where orbits settle, atmospheres thicken, and surfaces learn the rhythm of their stars. From the right vantage the whole story fits in a single frame. A graphite bright spine bisects the disk, two smoky rivers of gas pour inward along offset lanes, within, a muted oval pools with light, stippled by hundreds of hot crescents, protodisks catching fire where dust piles and cools. No neon, just thermal glow and scattered starlight, the color of iron at first heat. But the still image understates the intrigue. The bar is exchanging angular momentum for options, trading disorder for scaffold, writing temporary truces between gravity and feedback so that chemistry can slow down and try ideas. Not every cycle will gift a climate, not every ring will raise a stable archipelago of worlds, yet the odds change precisely because the bar keeps time. In a universe where chance rules the small scales, a straight bright scar across a spiral can be the closest thing to intention you will ever see. Tilt the frame and the geometry explains the timing. Two families of closed stellar paths crisscross the inner few kiloparsecs, the long, bar-aligned streamlines that carry most of the torque, and the short, perpendicular loops nested near the center. Gas cannot follow crossing orbits without colliding, so it chooses. It rides the long tracks until the inner resonances, then swings onto the short ones and piles up where the switch is smoothest. That is why the star-forming oval sits just inside the dust lanes and why the hottest newborn clusters march like pearls with an age gradient around the ring, compressed first at the contact points, older downstream as feedback hollows their cocoons. Offset tracers tell the same story in different languages. CO peaks where the squeeze is fresh, H-alpha and P-alpha flare a little further along, warm dust glows still later where winds and radiation have cleared the skin. If you map polarization, you catch magnetic fields draped along the shocks like pulled taffy, then curling inward with the streamlines. If you listen in radio continuum, you hear the flattening of spectra where fresh electrons are stirred and the softening halos where they age. Bars do not only feed, they also edit. By shuttling the cold phase inward, they starve the mid-disk and replace patchy chaos with orderly shear, shutting off giant cloud formation along the bar itself while igniting it at the ring. Quenching and triggering, written side by side on the same canvas. The metallicity slope flattens as recycled material is mixed toward the core, dust-to-gas ratios rise, the opacity of disks born in this season jumps just enough to cool midplanes efficiently and widen the safe corridor for solids to settle. In those opaque nurseries, turbulence declines from roar to whisper, the Stokes numbers that control drift slip into the sweet spot, and streaming instabilities switch on in thin, contiguous bands that ladder up from pebbles to mountain-sized seeds. The same secular torques that once threatened to drag giants inward now carve pressure dams that hold them, confining their gravity wells to the outer workyards and preserving the quiet inner lanes where smaller worlds assemble. Time itself becomes a parameter you can almost measure in the light. When the pattern speed sags, corotation migrates outward and the ring follows, leaving behind a fossilized, rotation-supported pseudo-bulge that still remembers the bar in its flattened, disky kinematics. Catch a galaxy mid-breath and you may see a nested relay, an inner, faster bar turning inside the older one like a gearbox, to ferry gas the last few hundred parsecs. Catch it later and the relay is gone, the central mass has risen just enough to undermine the backbone orbits, and the bar relaxes into a softer oval while the disk regathers asymmetries for the next attempt. Each loop of the cycle redraws the odds for climate, noise, then nurture, then a plateau long enough for oceans to equilibrate and for atmospheres to learn local weather instead of warfare. Even the rare hazards lean toward nuance. A compact black hole flicker fed by the bar's last inward gasp can loft a warm molecular breeze that dusts the cavity and trims the fuel line without blasting the ring. Superwinds from clustered supernovae prefer the minor axis, venting perpendicular to the plane and sparing the sheltered inner few hundred parsecs. The net effect, more often than not, is housekeeping rather than catastrophe, an enforced pause that lengthens the calm between bursts. In that pause, water finds its routes through damp snowlines, organics survive UV long enough to polymerize, volatile budgets become a book that can finally stay balanced. Pull back to the promised visual and the physics keeps its elegance. A straight, iron-hot spine bisects the disk, two smoky rivers pour along offset lanes, inside them an oval pool of light is stippled by 100 tiny crescents, protodisks warmed from within, not painted by neon, each a slow centrifuge weighing futures. The intrigue is in the motion you cannot freeze, angular momentum flowing outward, metals and dust flowing inward, feedback venting upward, chemistry settling downward. Call the bar a pump if you like, what it really sells is time, hard-won, locally ordered, statistically generous time, so that a restless galaxy can occasionally host something patient enough to call the result a season and the season a home. Across cosmic time the bars offer changes. Early disks were hot, clumpy, and thick. Torques came from massive knots that crashed inward and burned bright, a fast, violent way to feed centers. As universes aged and disks cooled, long-lived spines took over. The fraction of galaxies with strong bars climbs in the nearby epoch. Just when metallicities are higher, dust is more abundant, and disks can hold a rhythm instead of a riot. That shift matters because the warm window is not just about distance from a star, it is about the background pace. Bars deliver gas in pulses and then dim, and late-time bars tend to dim into quieter neighborhoods, UV fields down, cosmic ray pressure softer, turbulence subsonic, conditions that lengthen disk lifetimes and let atmospheres keep what they earn. You can test the storyline in light that cares about motion. Along each dust lane the shock bends starlight and reddens it over scales of only tens of parsecs. Just inside, CO filaments curl into the ring, and a few hundred parsecs further along, Pi-alpha and Br gamma beads flare where clusters have just shed their cocoons. Farther yet, warm dust glows at 24 micrometers as supernovae start to clear the skin, and non-thermal radio brightens where electrons are still young. Outer rings at the bar's far resonance hang like faint halos, signposts that angular momentum has been parked at the rim. Map polarization and you watch fields combed flat along the lanes, then corkscrewing inward with the streamers toward a circumnuclear disk the size of a small galaxy's downtown. Each tracer is a clock, read enough of them and the cadence of burst and lull resolves like a double heartbeat. Under the hood the bar writes small rules that become large outcomes. Pressure bumps at opacity and snowline transitions trap solids, Rossby waves at the edges of those bumps spin up vortices that warehouse pebbles, ambipolar diffusion and weak ionization clip the wings of magnetorotational turbulence just enough to keep midplanes thin. Streaming instability wakes once solids load the gas to the right fraction, and kilometer bodies appear quickly enough to outrun drift. In bar-fed, metal-rich disks, cores grow but stop at the traps they helped create, and hot Jupiters that would have bulldozed inner real estate remain marooned at safe distances. Photoevaporation, once a scythe in harsh starbursts, turns into a gardener. Disk winds peel only the lofted froth, leaving the dense midplane to finish its slow centrifuge. Even the hazards tend to be directional rather than absolute. Bar buckling heats orbits vertically for a spell and thickens the spine, but most feedback vents up the minor axis, away from the ring and the nestled systems inside it. Modest black hole flickers lift warm molecular breezes that dust the cavity and trim the inflow instead of detonating it. A compact central mass can weaken or even dissolve the bar for a time, and that sabbatical itself becomes a gift, a longer plateau of ordered gas, weak tides, and durable climates before the next relay sprouts. Pull the camera back to the promised scene and the physics stays legible without neon. A graphite bright beam cuts the disk. Two smoky rivers of gas pour along offset lanes toward an inner oval that shines like a low ember. In that oval, hundreds of tiny crescents glow, protodisks catching their own heat, some ringed, some striated, most tilted a little by the local shear. The arms hitch to the bar's ends and ferry energy outward, metals, dust, and stories stream inward. Between those crossings lies the interval that living chemistry likes, not silence, but a steady hush after thunder, long enough for oceans to find levels and skies to learn weather. The bar didn't make life, it made time with a preference, and in a restless galaxy, preference is the closest thing to mercy. Zoom closer and the age gradient turns into a time-lapse. Clusters at the contact points carry blue, hard light and sharp H2 shells. A quarter turn downstream the light warms as winds hollow the cocoons, another quarter and supernovae have carved chimneys that vent vertically, leaving behind calmer, redder knots that fade into a dust-rich oval. The elongated core keeps feeding the loop with fresh gas, but not uniformly. Its torque slackens and tightens as the pattern precesses, so the ring lights in patches that migrate like weather. Magnetic fields ride the flow, combed flat along the shock lanes and then spiraling inward, and their tension helps stitch filaments that refuse to shred. The result is order without stillness, streams that curve, clouds that merge, a racetrack where collisions are frequent but low speed, exactly the kind of traffic that favors collapse over carnage. In that inner commons the new systems inherit a chemical dowry that is richer than the mid-disk average. Dust mantles thicken, volatile ices cycle between vapor and frost, and grains accrete metal skins that make them tacky enough to glue on contact. Pressure traps at opacity jumps and snowlines collect solids into narrow belts, Rossby eddies at the belt edges hoard pebbles, streaming instabilities wake and promote piles into kilometer seeds before drift can steal them. Cores climb the mass ladder quickly, but the same pressure dams that built them also act as brakes, catching would-be giants before they surge inward and overturn the inner lanes. With the glare from massive neighbors already tapering and the cosmic ray bath relaxing after the burst, atmospheres that condense on these worlds stand a chance of keeping what they gather. The warm corridor, weeks to months of orbital period for modest suns, stops being a knife edge and widens into a shelf. The straight axis also edits the disk beyond the ring. Along the stellar bridge itself, shear is high and turbulence is oddly disciplined, giant clouds struggle to survive there, so star formation skips the spine and blooms at its ends and inside its oval. That division of labor writes two signatures at once, quenching in the bar proper, ignition at the resonances. Over repeated cycles the process flattens metallicity gradients and fattens a rotation-supported central component that remembers the bar in its kinematics even if the spine weakens. When the pattern slows, corotation marches outward and the outer ring at the far resonance grows, faint, broad, and metal-mixed, a record of where angular momentum was parked. The inner ecosystem keeps most of the benefits, a steady inflow, a softening background, and long, relatively quiet intervals where disks live out their viscous clocks. Hazards remain, but they acquire direction and timing. Bar buckling heats stars vertically for a season and thickens the spine, yet most feedback still vents up the minor axis, sparing the plane. A compact central flare, if the inflow briefly kisses the last resonant barrier, tends to be dusty and local, more of a warm molecular breeze than a scouring blast. Even encounters help more than they hurt. A passing dwarf or a tidal nudge can strengthen the stellar truss, freshen the lanes with new fuel, and reset the cadence without erasing the inner order. The worst outcomes require bad luck and bad phasing together. The typical outcome is housekeeping that lengthens the lull that chemistry prefers. Look again at the promised frame and the physics stays readable. A graphite bright beam runs through the disk, two smoky rivers descend along offset lanes, inside, an oval pool glows like banked coals. Across that pool, hundreds of tiny crescents shine, protodisks lit by their own friction and by warm dust, some laced with rings where pressure has penned the solids, some showing bars and spirals of their own where self-gravity has begun to write smaller copies of the larger script. Nothing garish, just thermal light and scattered starlight, the palette of iron at first heat and dust near sublimation. Follow the money, the angular kind, and the ledger explains the odds. The elongated hub steals angular momentum from gas and gifts it to stars outside, the arms carry that gift outward, thinning chaos at the center. The ring spends the inflow on clusters and on the quiet machinery of planet building, feedback pays a tax upward and buys clearer skies. The pattern slows and the cycle resets. Each loop is a negotiation between gravity, dissipation, and memory. None of it guarantees a climate, but it stacks probabilities in a way that blind, unbarred drift rarely does, more metals where you need them, less turbulence when it counts, pressure traps in the right places, and time, precious, statistically unusual time, for oceans to find their level and skies to learn stable weather. Even failure leaves useful fossils. A spine that grows too efficient can undermine its own orbit family and relax into a softer oval. What remains is a flattened, fast-rotating center with a dust-rich ring that still does the job. A lull that stretches into a billion years cools the background far enough that thin disks survive long after their luminous parents fade. A late relay, a short, faster inner bar, can reignite the lanes and finish the delivery to a tiny circumnuclear disk without waking a full storm. The script is modular, and Galaxies rewrite it with local accent, but the theme holds. A straight scar across a spiral rearranges chaos into cadence and trades brightness now for survivability later. From that vantage, calling the bar a pump is not metaphor but mechanics. It takes disordered orbital energy and exports it, it concentrates raw material where orbits are kind, it opens a window after thunder when the midplane is cool, the radiation polite, the chemistry unhurried. If life anywhere needs a patient hour in a restless city, a luminous spine across a disk is how the city buys it, an engine that prefers sequence over spectacle and builds, in its pauses, the possibility of a home. Tip the lens to the outer disk and you catch the other half of the bargain. At the bar's far resonance the traffic circle widens into a faint, gauzy ring where angular momentum is parked like cargo at the rim. Clouds there are stretched, not crushed, star formation is patchy, slow, and metal poor compared to the inner oval. That contrast matters, the outskirts remain a cold reservoir feeding the next innings, while the center refines and assembles. A minor tidal nudge, an offhand brush from a passing dwarf, can straighten the spine, tighten the lanes, and send a fresh pulse inward without igniting a full storm. Secular evolution becomes choreography, energy shuttled outward, mass ferried inward, pattern speed easing down, resonances stepping to new radii, and the whole system learning a slightly different rhythm with every lap. Inside the ring, kinematics whisper how gentle the favorable seasons are. Velocity dispersion drops in the midplane, not to silence but to a hush that lets grains settle, epicycles still exist, yet their swirls are small enough that pressure bumps hold their cargo. Ionization stratifies, tenuous skin active and windy, dense belly cool and calm. Ambipolar drift slides fields through neutral gas like hands through silk, diffusing just enough magnetic stress to keep shear from shredding the midplane. Chemistry exploits the lull. Carbonates condense at warm borders, organics polymerize instead of pyrolyzing, sulfur cycles without erasing water. The inventory that worlds need, volatiles, metals, catalysts, arrives in proportions that make geologies varied and skies stable, the two conditions most correlated with long-lived surfaces. Closer to the spine, the stellar backbone edits orbits in 3 dimensions. A brief buckling phase lofts stars above the plane and leaves behind a peanut-shaped kernel whose rotation still remembers the bar's cadence. Stripped of much of its cold gas, the spine becomes a truss rather than a nursery, it carries torque, not cradles. That division of labor is why the postcard shows emptiness along the bar and fireworks at its ends and inside its oval. Quenching and ignition sharing a single mechanism is not a paradox but a feature, the same ordered shear that forbids giant clouds in the bridge hurts gas toward resonances where collapse is inevitable and productive. Not every relay ends softly. A central mass can grow steep enough to scramble the orbit family that props the spine, and the bar will relax into an oval. Yet the fossils it leaves, the flattened, rotation-supported core and the mixed metal inner few kiloparsecs, keep doing the quiet work. They mint clusters, host long-lived disks, and buffer feedback so that the next pulse arrives as rain rather than hail. When a short, faster inner bar sprouts, it is a whispering gearbox, not a siren, a few hundred parsecs of extra torque that finishes the delivery without bringing back the thunder. Those episodes, stacked over hundreds of millions of years, are how a restless galaxy writes patient chapters, intervals long enough for climates to equilibrate, oceans to redistribute heat, and atmospheres to learn local weather instead of surviving local war. Frame the scene once more and let the intrigue sit in the physics you can nearly see. A straight, iron-bright scaffold bisects the disk, 2 muted rivers of gas curl inward along offset lanes, an inner oval smolders like banked coals, across it, hundreds of tiny crescents glow with their own heat, some ringed where pressure arrests drift, some striated where self-gravity has begun to draft miniature bars and spirals. Energy flows outward, matter flows inward, feedback vents upward, and chemistry settles downward. The elongated hub is not a flourish, it is a preference machine, taking a messy city of orbits and for a while choosing arrangements that favor continuity over spectacle. In those chosen intervals, chance stops feeling alone. The window for temperate worlds widens from a sharp ledge to a gentle shelf, and a spiral with a scar across its heart quietly becomes a better host for time. Statistical hints gather when you stack many barred cities at once. Metallicities run flatter inside the inner few kiloparsecs than beyond, rings host clusters with tidy age gradients, dust lanes stay razor-thin and offset, betraying shocks that never quite sleep. In integral field maps the gas spins on one rhythm while the stars hum on another, and the beat difference marks the pattern speed. Most spines end just shy of corotation, fast enough that arms hitch to the tips and ferry energy outward, slow enough that gas can still feel the pull and slip inward along the leading lanes. Where corotation drifts, the whole orchestra retunes, the ring walks, the contact points migrate, and last year's hotspots cool into today's red knots. Follow the manifolds around the bar's saddle points and the traffic plan pops into view. Trajectories that graze the Lagrange gateways peel into streams that either escape to the arms or spiral down toward the inner oval. Dust rides these highways like smoke tracing wind, announcing every bend with a kink and every shock with a sharp, dark edge. Inside the inner resonances, the closed family of short, central loops, those perpendicular orbits that gas prefers once the geometry flips, builds a compact, rotating disk that acts as a staging yard. From there, only a few hundred parsecs remain to the very center, and those last steps are governed by quieter gear, a small, faster relay bar if one exists, spiral dust fingers if it doesn't. Simulations that start messy and gas-rich end up writing the same choreography by themselves. Stir a young disk until it grows a spine, feed it, let feedback blow chimneys, slow the pattern, repeat. Each round trims the metallicity slope, fattens a rotation-supported core, and lengthens the intermission between roars. Crucially, the intermission is not empty. Turbulence decays from supersonic to gently transonic, the sound speed falls, the scale height shrinks, pressure traps sharpen at opacity jumps and snowlines. In that regime, solids stop behaving like free dust and start behaving like freight, captured, warehoused, advanced along belts and vortices until gravity signs for delivery. The exoplanet arithmetic changes with that logistics plan. High solid-to-gas ratios build cores quickly, but pressure dams that form from the same physics keep those cores from stampeding inward. Temperate corridors cease to be narrow ledges and become terraces, weeks to months orbits for modest suns with midplanes cool enough to keep volatiles, warm enough to keep oceans mobile, quiet enough that atmospheres don't boil away in tantrums. Giants still grow, but they loiter at the shelves that raise them, shaping outer climates while leaving inner lanes in peace. When giants do wander, they do so after the burst, through thicker, cooler air, in migrations that reshape but do not raise. The hazards never vanish, they line up. A buckling episode thickens the bar into a peanut-shaped kernel and sends a brief rain of vertical heating through the inner disk, but most of the fury vents up the minor axis. A compact accretion flicker at the very center floods a few hundred parsecs with warm molecular light and then starves, trimming the inflow without kicking the door off its hinges. A passing dwarf tweaks the pattern, freshens the lanes, perhaps even kindles an outer ring at the far resonance that stores the angular momentum the inner city just exported. None of these are guarantees, all of them are biases, small tilts that make the calm last longer than it would by accident. Even the color palette tells on the physics without resorting to neon. Iron first heat at the spine, soot dark at the shocks, ember red in the ring where dust glows and newborn clusters push back their cocoons, faint amber along the arms as they carry the bar's surplus into the outskirts. Inside the oval the crescents multiply, slender arcs where rings and gaps have penned solids, thicker halos where accretion is still hot, occasional bars and spirals inside disks where self-gravity has started to write miniature copies of the grand design. It is a quiet blaze, readable at a glance and inexhaustible on closer inspection. Time scales stack like nested clocks. Tens of millions of years for a ring to light and drift, hundreds of millions for a pattern to slow, a relay to sprout, or a spine to relax, a billion for gradients to flatten into memory and for a rotation-supported center to take on a life of its own. Habitable intervals sit between these gears, longer than the flare of a single burst, shorter than the depth of the pattern, long enough for oceans to equilibrate and for skies to invent weather instead of survive it. What bars sell, in the end, is not certainty but duration, ordered stretches in noisy neighborhoods, stretches in which chemistry can finish sentences it usually has to abandon. If you want a field test, listen in multiple languages at once. CO maps flag the fresh squeeze, recombination lines mark the cohorts that just came of age, mid-infrared bands from aromatic carriers trace the relit skins after shocks, radio continuum hardens where electrons are new and softens where they have aged, polarization lines up along lanes and then spirals inward with the flow. Lay those tracers over the starlight and the cadence appears like a heartbeat with a pause between beats, a pulse and a rest, delivery and digestion. Pull back once more to the promised frame, a straight, luminous truss cutting the disc, two muted rivers pouring inward along offset lanes, an inner oval glowing like low coals, across it, hundreds of hot crescents, small laboratories spinning down their chaos into structure. Energy leaves, matter gathers, winds climb, chemistry settles. Call it a pump if you want, it is equally a metronome. In a universe that prefers turbulence, a bar persuades a spiral to keep time, and in those counted measures the odds tilt, slightly, stubbornly, toward worlds that can warm without burning and last long enough to remember. Tip the simulation a notch further and the mechanics read like a recipe. The long, bar-aligned orbits, call them the spine family, carry most of the torque, the short, perpendicular loops inside, call them the heart family, collect the inflow. Gas, forbidden to cross itself without shock, slips along the spine until the inner switches appear, then folds onto the heart loops and stalls just long enough for gravity to steal the show. There, surface densities clear the instability threshold, sheets shred into filaments, filaments bead into clumps, clumps shear into hundreds of compact centrifuges that glow as pale crescents against a warm floor. Dust mantles thicken, ices cycle at their snow lines, and pebbles drift until pressure traps at opacity jumps and dead zone edges hold them like shelves. Vortices bloom at the trap rims, streaming instability wakes, kilometer bodies appear before drift can rob the bank. The same pressure dams that built the cores catch them, too, and what might have become marauding giants hangs back on the outer terraces, leaving the inner lanes to sketch smaller, temperate plans. Observables keep the ledger honest. Dense gas tracers spike just inside the dust lanes, shock fingerprints in CO and Fe2, sharpen where the squeeze is young, recombination lines bead slightly downstream, PAH bands reignite further yet as skins recover, radio spectra harden where electrons are fresh and soften where they age, polarization vectors lie flat along the lanes and then spiral into the oval. Pattern speed sets the cadence. When it sags, corotation walks outward, contact points migrate, and the ring's hotspots drift like weather on a slow jet stream. Outer arms hitch to the bar tips and ferry energy outward, raising a faint far ring that warehouses angular momentum at the rim, inner flows curl inward like smoke following a draft, and the downtown fattens into a fast-rotating kernel that remembers the spine long after it fades. Habitability is a matter of background manners. During the roar, UV fields, shocks, and cosmic ray baths are blunt instruments, excellent for chemistry's inventory, cruel to young atmospheres. In the lull, the atmosphere of the inner few kiloparsecs turns civil. Turbulence slides from supersonic to transonic, sound speeds fall, scale heights shrink, ionization stratifies into a windy skin and a cool belly, ambipolar drift bleeds magnetic tension without tearing the midplane. Disk winds peel froth and leave the dense waste to work, photoevaporation trims, not scythes. Metallicity and dust-to-gas ratios sit in the sweet spot where midplanes cool efficiently and pressure bumps stay sharp. The corridor 4 warm orbit ceases to be a cliff and becomes a shelf, weeks to months periods around modest suns where water can stay liquid, volatiles can cycle, and skies can keep what they are given. The bar edits architecture beyond the ring as surely as it feeds the center. Sheer along the stellar truss is high and disciplined, giant clouds seldom survive on the bridge, so star formation leaps to the ends and into the oval. Quenching and ignition share a cause, ordered torque that forbids one locale while forcing collapse in another. Over cycles, gradients flatten, a rotation-supported core fattens, and the intermissions lengthen. Even interruptions lean helpful. A short, dusty nuclear flicker lifts a warm molecular breeze that vacuums the cavity and chokes the inflow before a full storm can form. A mild buckling season thickens the spine yet vents fury up the minor axis, away from the cradle. A passing dwarf tweaks pattern speed just enough to refresh the lanes without wrecking the stage. Cinematically, nothing gaudy is required. A graphite bright beam cuts the disc, two smoky rivers stream along offset lanes, inside, an oval smolders like banked coals, across it, hundreds of crescents glow, some narrow with rings where pressure pens solids, some thicker where accretion still runs hot, some already sketching tiny bars and spirals of their own. Energy flows outward, matter flows inward, winds climb, chemistry settles. The intrigue is in the invisible current, angular momentum traded for options, noise traded for cadence, brightness now traded for survivability later. A bar does not promise life, it sells duration, measured, statistically generous seasons in which disks can finish their bookkeeping, oceans can find level, and skies can practice weather instead of war. In a universe that prefers turbulence, a straight luminous scar persuades a spiral to keep time, and in those counted measures you can almost hear probability tilt. Push the clock forward one more beat and the city redraws its lanes. As the pattern slows, corotation migrates and the contact points slide, the ring does not switch off so much as relocate, leaving behind a fossilized, rotation-supported kernel with disky kinematics and a memory of straight lines. The fresh oval lights where the new inner resonances settle, and the same choreography resumes with a different radius, shocks along the leading lanes, dense gas spikes just inside them, age gradients that march around the oval like hours on a dial. Between these resets the background manners improve, radiation fields soften, turbulence tapers, and the midplane compresses, so the next cohort of disks begins with higher metallicity, sharper pressure traps, and gentler stirring. The corridor for temperate orbits thickens from a ledge to a terrace, and cores that would have plunged inward in a riot now meet pressure dams that stall them into quiet architecture. Habitability, in this script, is an emergent property of patience. The bar manufactures patience by turning violent inflow into paced delivery. Zoom into a single crescent and the small physics rehearses the large. Pebbles drift inward until a snow line or opacity jump slows the gas and creates a shelf, solids pile, vortices bloom, streaming instabilities wake, planetesimals appear before drift can bankrupt the account. Ionization stratifies so that a windy skin can vent while a cool belly stays laminar. Weak magnetized winds bleed angular momentum without shredding the midplane. Young atmospheres condense while the fireworks are already venting up the minor axis and away from the plane. Cosmic ray baths that once scoured the ring slacken with the dying burst, and escape velocities begin to win. Giants still grow in the outer workyards, but the same shelves that raised them keep them there. Inside, months-long orbits around modest suns stop living on a knife edge and learn weather. The promised image remains honest without neon. A straight, iron-bright truss spans the disk, two smoky rivers of gas stream along offset lanes, within, an oval pool glows like banked coals. Across that pool, hundreds of tiny crescents shine, some narrow and ringed where pressure has penned the freight, some fat and veiled where accretion is still hot, a few already sketching miniature bars and spirals under their own self-gravity. Angular momentum leaves by the arms, metals and dust arrive by the lanes, feedback climbs out of the plane, chemistry settles to the midplane. The intrigue is the ledger you cannot see, torque converted into structure, brightness spent to buy duration, chaos negotiated into cadence. A bar does not guarantee life, it engineers intervals in which life is statistically less unlikely, carving seasons of gentle background in a city that otherwise prefers storms. In a universe that loves turbulence, a straight scar persuades a spiral to keep time, and in those counted measures, worlds get to try ideas long enough to remember them. Tip the telescope to chemistry and the lull sharpens into a laboratory. The inflow salts the inner kiloparsec with fresh metals and dust, so cooling times shorten and clouds reach higher densities before feedback can bite. Grain mantles cycle through frost and vapor at snowlines that now sit closer to the star, plating pebbles with sticky skins and raising the collision efficiency that turns sifted dust into freight. Carbon chains survive shocks better when the background UV is down. Nitriles and simple alcohols last long enough to seed the next steps. Sulfur stops behaving like a vandal and starts acting like a catalyst. The mid-plane, thin and slightly magnetized, becomes an assembly belt with built-in quality control. Pressure shelves pin the inventory, vortices warehouse it, and weak winds keep the belt moving without rattling the cargo. Kinematics sketch the quiet in numbers that feel like weather. Velocity dispersions sag to the low tens of kilometers per second in the gas. Shear remains high where it should, along the stellar truss, but inside the oval the flow curves, not clashes. Oblique shocks at the lanes still write crisp edges, yet just inside, line widths narrow and the rotation curve turns velvet smooth. Pattern speed sets the tempo. As it eases, the resonance radii walk outward and the ring follows, the contact points drifting like a slow front across a continent. Each relocation inherits a richer mixture, flatter abundance gradients, higher dust to gas, so every new cohort of disks begins a little cooler, a little stickier, a little better at holding on to what matters. Architecture responds with restraint. In the outer workyards, cores fatten quickly on pebble diets, but pressure dams that helped build them also arrest their march, leaving would-be giants loitering where they sculpt climates without raising inner streets. Inside, months-long orbits around modest suns graduate from knife edge to terrace, enough irradiation to keep oceans moving, not enough tantrum to boil skies. Dead zones bloom at the right radii to mute turbulence without stopping accretion. Magnetized breezes peel only the froth and spare the dense waste where atmospheres thicken. A skyline of small worlds is more likely than a few bullies. Multiplicity replaces melodrama. The stellar backbone keeps editing the city as it feeds it. Along the bar proper, ordered shear suppresses giant clouds, star formation dodges the spine and blooms at its tips and in the oval it supplies. Quenching and ignition read as opposites in photographs and as cause and effect in dynamics. Over cycles, the center flattens into a fast-rotating kernel that remembers straight lines in its orbits even after the truss softens. Metallicity slopes level, the intermissions lengthen. A mild buckling season thickens the spine into a peanut-shaped core and vents heat up the minor axis, away from the cradle. A dusty central flicker trims the fuel line rather than detonating it, buying the ring a longer, softer afterglow. Even the outskirts take a role that makes the whole sustainable. At the far resonance, a faint outer ring stores the angular momentum the bar exported. It is a reservoir that keeps the inner pump from starving and a brake that keeps the pattern from racing. Arms hitched to the bar tips ferry energy outward like tethers. Small asymmetries, refreshed by tides or lopsided accretion, keep the spine honest. When the pattern slows too far and the orbit family that props the truss begins to fail, the city coasts on its rotation-supported memory until a new relay sprouts. Secular evolution is not a single event, it is a habit. Observables line up like instruments in an orchestra you can hear with the right receivers. Dense gas tracers spike just inside the dust lanes, shock fingerprints sharpen at the kinks, recombination lines bead along the ring with a clean age gradient. Mid-infrared bands relight the skins after the squeeze, radio spectra flatten where electrons are fresh and soften where they age, polarization vectors lie along the lanes and then twist inward with the flow. Stack those maps and the cadence appears, delivery, digestion, delivery again, each beat slightly slower, each rest slightly longer, each cohort of disks beginning under gentler manners. Drill down to a single crescent and you still find the bar's signature. Rings and gaps mark where pressure has penned the freight, a soft wind lifts only the high-altitude chaff, the laminar belly carries pebbles inward until a snowline arrests them and a vortex banks the pile. Streaming instabilities wake at the right load, kilometer seeds arrive before drift can embezzle the account. Cores assemble, atmospheres condense, and the fireworks that once threatened them now vent orthogonal to the plane. The difference between catastrophe and climate is rarely a new ingredient, it is timing. The truss manufactures timing. Pull back to the frame and nothing garish is required. A straight, iron-bright scaffold cuts the disc. Two smoky rivers of gas pour along offset lanes. An inner oval smolders like banked coals. Across it, hundreds of small crescents glow, thin where pressure pens solids, thick where accretion still runs hot, a few already showing miniature bars and spirals under their own gravity. Energy leaves by the arms, matter gathers by the lanes, winds climb out of the plane, chemistry settles to the midplane. Call it a pump, a metronome, an auditor, it trades angular momentum for options and brightness now for duration later. In a universe that defaults to turbulence, a luminous scar persuades a spiral to keep time, and in those counted measures the odds tilt, quietly and persistently, toward worlds that can warm without burning and last long enough to learn their own weather. Turn the camera into prediction mode and the script starts offering tests. If bars really manufacture patient seasons, then ring-borne systems should skew toward compact, multi-planet architectures with low eccentricities and modest mutual inclinations, chains that hint at pressure shelves and gentle migration rather than bull-in-a-china shop giants. Hot Jupiters should be rarer for these cohorts because the same dams that helped fatten cores also stalled inward rush. Warm giants marooned at exterior traps should be the typical heavyweights, shaping climate from afar instead of raising inner streets. Atmospheres on inner small worlds should carry the signature of a tempered nursery, higher metal hydrides early, then a slow tilt toward water and CO2 as photoevaporation eases and delivery trickles in across cooled snowlines. None of this requires miracles, it only requires a background that calms down on schedule. Observables line up in layers that cross-check each other. Steeper age gradients along the inner ring than along the arms, but with softer UV fields a quarter turn downstream, dense gas tracers spiking just inside dust lanes, then a clean handoff from H2 lines to warm dust bands to non-thermal radio as clusters mature, polarization vectors combed along shocks and spiraling inward across the oval, metallicity slopes flatter in the inner few kiloparsecs than beyond, with dust-to-gas ratios just high enough to sharpen pressure shelves. Stack those maps over stellar kinematics and the pattern speed drops out of the difference between the gas beat and the star beat. Watch that speed sag across a sample and the resonances should walk outward with it, pulling the ring and its age dials along like a tide. Drill back into the crescents and the microphysics echoes the verdict. Streaming instability does not need heroics when solids are pre-sorted, vortices at shelf edges warehouse pebbles, magnetized breezes lift only froth, and the midplane, thin, cool, slightly ionized, lets kilometer bodies appear before drift can embezzle the account. Dead zones turn turbulence from roar to murmur without freezing accretion, snowlines plate grains with sticky skins that boost collision efficiency by quiet percentages that compound. Giants still happen, but their wakes are gentler, their migrations later and slower, their final parks at the very shelves that raised them. The inner lanes, spared the stampede, sketch delicate plans and have time to revise them. Even the failure cases teach the rule. A central mass that grows too steep can unravel the orbit family that props the spine, the bar relaxes into an oval and the lanes go soft. Yet the rotation-supported kernel it leaves behind keeps the downtown orderly, and the mixed metal inner disk continues to mint long-lived systems under calmer skies. A buckling episode thickens the spine into a peanut kernel, vents heat up the minor axis, and, counterintuitively, buys the ring a longer intermission. A dusty nuclear flicker trims the fuel line without detonating it. A tidal nudge from a passing dwarf tightens the truss and refreshes the streams. Catastrophe is possible, cadence is common. Run the time-lapse in your head. First beat, a bright truss bites, shocks light the lanes, a ring kindles, clusters bead, chimneys open. Second beat, the background softens, turbulence eases, the midplane thins, crescents multiply and sharpen as pressure pens the freight, warm corridors widen from ledges to terraces. Third beat, Pattern speed sags, resonances migrate, the old ring fades into a memory kernel while a fresh oval ignites at a new radius, inheriting better metals and thicker dust. The intervals between beats lengthen. The metropolis is still restless, but its seasons become readable. And the visual you asked for keeps telling the truth without neon. A straight, iron-bright bar cleaves the disk. Two smoky rivers bout inward along offset lanes.